We will now have Roberto Vega talking about the relationship between resurgence and isomonodromy in Painlevé equations, please.
Thank you very much for the introduction, and thank you very much for the invitation to talk up in this workshop. So let me tell you a little bit how this talk is going to go. So we basically worked a lot on what we call direct resurgence on the Painlevé equation. This means get these Painlevé equations and bang them with resurgence theory until they produce something. In this case, normally numerics that led to closed form versions of this Stokes data that Max was talking about. But then Professor Iwaki told us that this should match against isomonodromy computations that have been kind of not known to the physics community for a long time. And we decided to take a look into this. And I'm, of course, talking about the isomonodromy works of Aoki, Kawai, Takei, who is here today in the audience. So let me just review these things a little bit and tell you a little bit more on how this connection works. But of course, the title of this conference is Physical Resurgence on Quantum Gauge and Stringy, and that's why I'm going to talk now a little bit about the stringy part of it, and then I'm not going to mention it again until the end of the talk. It's just to have an excuse to be in this conference. So, of course, this talk is going to be based on the work that already Max mentioned, and in collaboration with Salvatore Baldino, Riccardo Schiappa, who is our supervisor, and myself. And then I will talk a little bit more in the case of the inhomogeneous Painlevé equation, so the one that has this alpha parameter turned to be non-zero. This is going to be a little bit more based on the work that I've been doing lately, that it's still not published. So motivation, what's the motivation? So we know that in string theory, as Max was saying very neatly, perturbative contributions are kind of easily obtainable. And the non-perturbative contributions are the ones that are normally much harder to obtain. Of course, this depends on the setup, but I mean, let's say general string theory, easy string theories, you can do this. So we want to understand if there's a way of going beyond perturbative, that it's kind of easy. At least we can do something, even if we don't have a nice interpretation of it. So the simplest example that one can get is, of course, the case of 2D quantum gravity and the case of 2D quantum supergravity. And these ones correspond, as it's already known and it has been known for a long time, to the Painlevé I and the Painlevé II equations. But then if one tries to go to the next two leading simple examples, so just a little bit increment in difficulty, one has this, again, the same 2D quantum supergravity, but now one can turn on some background in the string theory, like let's say, for example, background Raman fluxes or some D0 branes. And now Klevanov, Maldacen, and Seiberg studied this theory in depth, and they found that this was given by some deformation or some Q deformed Painlevé equation. This has nothing to do with Q deformations. It's just that they call this the equation like this. So it's just a different equation. But now, if you see from the equation before, so now you can see here that you have the Painlevé equation is missing the alpha factor. So this would be what I'm going to be calling all the time the inhomogeneous Painlevé equations, just that this alpha is different from 0. And this alpha difference from 0 is interesting because even though it doesn't directly correspond or it doesn't fall automatically from the string theory, Klevanov, Maldacen, and Seiberg also studied that there's this thing called a Miura map, which basically is a map between the KdV hierarchy that is generated by the Painlevé I equation, and it connects this KdV hierarchy to the modified KdV hierarchy. And in particular, what it's interesting for us is that it relates this Q deformed Painlevé equation that we don't know a lot about, but it relates it to the inhomogeneous one, provided that alpha is somehow a shift in Q. So that's the reason that we are focusing more on the inhomogeneous Painlevé II equation is because it's much well known. More people are studying this than just the Q deformed version. So the last motivation for this thing is that even in this paper by these people, again, on this Q deformed theory, so Klevanov, Maldacen, and Seiberg, they wanted to understand this equation because it's very interesting. If you expand at z going to infinity and at z going to minus infinity, you get these two different sheets, two different normalizations of the perturbative sector, let's say. So you say, you see that For example, Professor Takei was talking the other day about the fact that the Painlevé II equation has a double sheet and a single cover. No, so in this case, they found a solution of this string theory that at large Z behaves like a closed string theory in presence of RR backgrounds, while at the negative side, so if you want to go from the positive to the negative, you find a theory that it's described by a background of QD0 brane. So this is like kind of a type of open-closed string duality, and we want to understand this a little bit more by using resurgence techniques and studying these systems a little bit better, and we want to understand what this means. And this is just a comment that I'm going to make in the end, but let's just start now. Of course, I mean, what am I going to do now? Resurgence matches isomonodromy, right? So this is the thing that we want to do. So we know that transition functions on Stokes data for Painlevé equations have been computed analytically. I mean, and this are the works of Aoki, Kawai, and Takei here, by means of the isomonodromy deformations and this exact WKB method. So we want to take these transition functions or these connection formula and try to find it from the resurgence point of view and see how can we connect the two of them. So let's just give a brief outline of what we're going to do. I'm going to explain a little bit what I mean when I say get the Painlevé equation and bang it with just resurgence. And then I'm going to explain a little bit about the transition function that we found by using the methods on the first paper. So basically just by banging the equation with resurgence. Then I'm going to talk a little bit about the isomonodromy results. It's just a little bit about remembering what was spoken on Monday here. And then again, I'll go back to resurgence for kind of a little bit newer results. And finally, some comments on the string theory that I was mentioning, this open-closed string duality. Okay, so let's just go with the transseries setup. So of course, we know that the Painlevé I equation, we know that how the perturbative ansatz look and so on. And the important part of this equation is that the series, at least the perturbative series, is asymptotic and it grows, and the coefficients grow up to as 2g factorial. So it's a nice setup for resurgence. Again, the inhomogeneous Painlevé equation has the same feature. It's just that now there's no one perturbative sector. There are two perturbative sectors. So one of them is a double cover, and you can see it on the first line because we basically have a square root, while the second one is just a single cover because it's 1 over alpha. And again, the Q-deformed Painlevé equation has the same features. It's just that now we have a fourth cover, which corresponds to the previous double cover if you do the Mura map, and then a double cover that it's the single cover in the Mura, if one applies the Mura map. So this is very much understood if one just basically explains a little bit the inhomogeneous case. So how do we perform resurgence in this context? So we get the equation, and now the things that we're missing are the non-perturbative terms. And how do we solve this? Because until now, we only have the perturbative series. We basically use these transseries ansatz. And then if one cares a little bit more about getting numbers out of these asymptotic series, one can perform these Borel-Laplace transforms, but we know that this only works sectorially. So this only works in a sector of the complex plane. And if we want to understand global solutions, now we need to understand the Stokes automorphisms, which basically tell us how to glue these sectorial solutions. And how can we obtain this Stokes data? Is very simple, just from the theory of resurgence. Max explained a little bit to you these large order equations that you can do, but I'm going to explain a little bit more on the numerical side, on the computational side. So if one can understand all the Stokes data, now we can construct transition functions, and we can try to check if these transition functions make any sense in the context of the theory. But also, we can try to see if with these transition functions, one can reproduce isomonodromy results. And again, and this is like the Painlevé I case is the one that is going to be better explained, but then we will try to do a little simple computation on the Painlevé II side. So the Painlevé I equation is a second order differential equation, and that's why we say that we have two instanton actions. And therefore, we normally use what we call a two-parameter transseries solution, and I will explain all the terms in here later. But if one studies the case of Painlevé II, even it doesn't matter if it's the inhomogeneous or the Q-deformed, you can see that now we have 4 actions for each equation. And this is very simple. There are 2 actions associated to the single cover and there are now the two actions associated to the double cover. And of course, double cover and fourth cover on the side of the Q deformed. But now we are interested in what I mean by these two parameter transseries solutions. So let me explain to you what are the context or the contents of this ansatz. So we start by having two initial conditions. These are like we have a second order differential equation. We need two initial conditions. And these initial conditions somehow label these non-perturbative terms that we have put there by hand to have this non-perturbative, to grasp where this non-perturbative information is. And you can see that sigma 1, for example, is to the raised to the power n, and that corresponds to the negative exponentials in this case. And the same follows for sigma 2. Then we have these logs here that they basically deal with resonance in this setup, because if you try to solve for the Painlevé I equation, you try to solve the recursion relation, at some stage you will find some problems, and this means that you have to introduce these logarithms to basically be able to solve this recursion relation. But in the end, these sectors are related to each other, so you can resum them into somehow some x power in this case, so some gs power raised to some gs raised to some power. And finally, we have the sectors, and these are the logarithm, these are the asymptotic sectors. So these are like the asymptotic series that one can resum. But as you can see here, now I see that I'm summing in a very special way. I'm summing first in m and then in n. So this means that somehow I'm summing like on the left-hand side of this slide. So I'm summing either first on rows and then in columns, or first in columns and then in rows. So I'm always summing first one of the ends and then the others. There's a different type of summing. So there's a different way of summing this transseries, which is basically caring a little bit more about the exponential weights. So if you go back a little bit, you see that these exponential weights, this is resonant. So basically it means that some sectors will have the same exponential weight associated to them. For example, the perturbative has 0, 0, has no exponential, but the non-perturbative 1, 1 also has an exponential that is exponential to the 0. So it means that both have the same exponential weight, even though they're associated to different things. So one can try to do this, and you can see here the 0, 0 and the 1, 1 in the same type of summation, and then try to go each time this represents, each line now representing exponential weight. So now not in this transseries resurgence point of view, but more a little bit on caring about the exponential weight. And this means that in here, the variables would be something like sigma 1 and sigma 2, but in this type of summation, the variables should be changed into something like the product of them, and then you can choose either one of them or the other, and you basically label going up or down by multiplying or dividing. So it's just for you to take into account that sometimes changing variables might be very useful, and you will see this in a minute. But now, okay, now we have the transseries and we know how the Borel-Laplace transform works. And now we want to really try to construct global solutions. And for that, we need to understand how to cross these Stokes lines. So I'm here, you can see that you have these Stokes configurations for Painlevé I, and then you have the Painlevé II ones for the single and the double cover. And basically, these Stokes lines are these limits in which our Borel-Laplace resummations need or undergo a jump that basically guarantees this continuity. Guarantees this continuity, not discontinuity, which is a different concept. So this Stokes automorphism tell us how to cross these lines. And this is what we are very interested in. And I'm just recalling a little bit what Max said before. There are two types of encoding the information of crossing this line. One of them is Stokes data, which is much simpler, and there are less of them. And then there are the Borel residues one, which are much more, but they are kind of simpler to understand. So in here, of course, you can see them. This is the Stokes automorphism. This is a Stokes automorphism. This is a special case just for readability. And here we have either the Stokes or the Borel residues. But again, Max also showed how to go from one to the other. So in practice, we don't really care which one we choose. And the important part here is that this structure that Max was presenting of this lattice that goes to -infinity and in both directions, this vector structure of these nice patterns on the diagonals and on the vertical lines, all this still holds for all the equations that I'm presenting today. So it holds for the Painlevé I, the inhomogeneous Painlevé II in both the double cover and the single cover, and the for Q deformed equation. So this is universal for all the equations that I'm presenting here. So when I say Borel residues, why do we call them Borel residues? Is because if one applies the Borel transform to one of these asymptotic series, of course, one gets a convergent in a radius of convergence. One gets the Borel transform has some singularities, of course, located at linear combinations of the actions. And if one takes a closer look at these singularities, in the case that we are analyzing, we find what we call simple resurgent functions. And Max talked a little bit about this, but this basically means that you have some Borel residue attached to the singularity, and then you have a pole that is normally connected to the initial coefficient, so the first coefficient of the Borel transform, and then you have the resurgence of a different sector to explain how the singularity behaves at this close to this singularity, and then the logarithmic branch cut. So how does this look in practice? So, in theory, right? Like you would ideally try to put these logarithmic branch cuts away from each other, and then you would enclose them into a Hankel contour to basically obtain this contribution of this Borel residue. But numerics tells you that you cannot move your branches away, and basically they get mixed to each other. So you have to like play around a little bit, but this is kind of the idea on how to do these computations. So this is more or less numerically how this works. And I'm saying this because I'm going to show some numbers later, and I'm not going to tell you how I computed them, but this is basically the method. And I just wanted you to have an idea of how the method works. So imagine that now we can compute all these Stokes data. This means that now we can construct these Stokes transitions. So how do they look? Well, the reason why I explained to you why we could just sum differently is because if you choose the correct variables, the Stokes transitions look very nice. So defining this mu that I said before, and if you define now this ρ0 or ρ pi, depending if you're looking at the forwards or the backwards transition, this ρ0 and ρ pi is just some of the sigmas multiplied by the degenerating function of the first diagonal. So if you look at the positive, is the blue first diagonal, and if you look at the negative transition, is the red first diagonal. And why are these quantities interesting? And you can see them here. It's just one of the transseries parameters times the first one, so the first Stokes in the lattice, and then we have this 96 square root of 3 that appeared in Max talk in this logarithm, and then there's a 1 over gamma function of 1 plus 2 mu over square root of 3. So this is kind of a weird way of writing this, or a weird variable to choose, but it's super interesting because if you do a Stokes transition, and this is what we found, if you do a Stokes transition at 0, ρ0 is an invariant of the transition. So if you define this quantity, which you can easily do because you have sigma 1, sigma 2, and then you can plug in sigma 2 here, mu here, then this quantity doesn't change before and after the transition. And furthermore, this quantity is relevant for the transition of the mu variable. So mu gets a simple shift that it's given uniquely determined by this ρ0 that doesn't change. So transition functions look very nice if you choose the correct variables. And this is something that it's very interesting. Of course, these square roots and 4 pi i's depend a little bit on the normalization of your Painlevé equation. And for example, if you do for Painlevé II, this is the homogeneous case and the double cover, then you find a little bit nicer numbers, but it's just a matter of conventions. So I've told you that the latter transitions are valid in the 0 or pi direction. But now we want to be able to go around any way on the Borel plane. So it means like going in this Riemann sheet either up or down. So this means that we need still to understand how are the transitions at 3 pi, 4 pi, and so on. And this is very easy because we can, the way in which we do it is if we are up on the Riemann sheet, we can go down, rotate our transseries back to the 0 or the pi directions, and then undergo the Stokes transition, and then go back again to the point in which we were. So we can like pull the whole transseries down, do our transition, and then pull it up. And when I mean pulling down, I mean that always you can do these rotations and encode them in the parameters sigma 1 and sigma 2. And this is very interesting because then you can use the 0 and the pi to generate any transition. And since you can generate any transition, you would say, okay, let's just go around to see what happens. And if you go around and see what happens, this is what Max was drawing before, you get these beautiful monodromy orbits. So you want to see, so we have now a couple of numbers and we have these transitions and we want to check what's a soft proof or a soft check that we can do on these transitions, right? So the minimum thing that one can require for them is that after a number of rotations, they close. So if you start with some random numbers, here minus 1.41, minus 2.16, and I just completely random generated these numbers, then after 1, 2, 3, 4, and 5 transitions, you go back again to the same number. So this is something that you would expect these transseries parameters to do. And unfortunately, these 5 rotations correspond to 4 rotations on the original variable. But we know that Painlevé I has a simple monodromy, so it's after 1 turn, you should go back to yourself. And we still don't know why this doesn't happen after only 1 turn, but we also know that the monodromy space of the Painlevé equation is not very simple. Like there are works by Okamoto that I'm not very familiar with, but I know that he has a lot of, he has been studying a lot this monodromy space for Painlevé equations, and it's not as simple as it looks. It's just a comment for, in case someone is interested. Yes.
Sorry, can I just ask a little bit of clarification? When you're talking about monodromy, you're talking about moving in the independent variable plane of the Painlevé equation.
Yes.
Right?
Yes.
And you've got these various things happening with the parameters.
Yes.
But what the Japanese authors like Okamoto studied was the monodromy plane of the corresponding linear problem.
Ah, okay.
So that's, I think, a different sense in which the word monodromy is being used.
I've never really was very much like these things that we did with monodromy. We basically finished them, and we were like weirded out by the fact that you couldn't reproduce the normal monodromy of the solution.
Yeah.
And then we assumed that had to do with some more mathematical strong problem. And the only thing that we knew about this type of monodromy space studies that were these Japanese works, but I've never seen them. Like I know that they exist, and I was like not very.
So perhaps a little bit of a quick way of thinking about them is that they're like a Fourier transform of the original equation, and so you're talking about what happens with singularities in the transform plane, rather than the singularity near the infinity, say, in the original plane.
Okay. Okay, I want thank you very much for the comment. I was not much aware of it. This is also interesting because these transition functions also have some places in which they blow up or they just go to 0, and they also don't have like a you find sometimes like there are special points in these transition functions. So it's also a very interesting moduli space from this point of view. It's just that I don't know the geometry of it. And if we do the same thing with the homogeneous case and the double cover, this is just because this is the case that we studied the most. We again see, and now we were lucky that this just basically closed after 2 rotations on the original variable. And I'm always taking out a square root global prefactor. So it means that this transseries has the same determination of a square root. And then it kind of, one hopes that it kind of cancels, but it's not very straightforward. So let's just say that after 2 rotations, we go back to the same point, which is not that bad. Yes.
Just a small comment. So it didn't have to be the case that after it didn't have to be a finite number of transformations to come back to yourself. So the reason for that is, as I mentioned earlier, so there is an underlying A2 cluster algebra. Yeah. And that's precisely the transition functions that you find are the ones attached to this one, and this has a finite.
Exactly.
So it comes back to itself after a finite amount of steps, but generically you would expect that maybe you have infinitely many.
Exactly. When we were doing these things, we were not, I mean, we're hoping that they would close at some stage, but we didn't have any reason for them to close. It's just that if it closes, it's kind of, okay, there's something here that it's not as bad. Like you can say, okay, I mean, they close, okay, some of the structure can be, it has to be okay in this sense. But of course, it's not necessary for this to close.
So there is an underlying n = 2 theory with a finite amount of BPS objects associated to this problem.
Nice.
So that's the reason why it closes after finite.
Oh, that's cool.
Or that's one way of putting it.
Oh, that's very cool. Thank you. So now, okay, so we have seen how the transition functions look from the just basically banging these equations with resurgence. So let's just talk a little bit about isomonodromy now. So, I mean, I'm just recalling a little bit, a very few details on the isomonodromy counterpart. So we know that there's this linear systems associated to the Painlevé equations, and these Painlevé equations arise as from the Hamiltonian system in this particular normalization. And now I'm going to choose alpha to be alpha 2 just for the sake of readability, and also because I want to use the original conventions from Aoki, Kawai, and Takei, in which our sigma 1s and sigma 2s are going to be alpha and beta. So I want to like change my alpha to alpha 2. And of course, the WKV solution of this linear Schrodinger equation can be studied by means of this by just basically doing this formal power series. And the interesting part is that it almost always diverges as a series in eta. And if we are able to do this Borel-Laplace resummation exactly, we can compute the resummation below and after the Stokes lines. And from here, one can get transition functions. And the nice part is that for the Painlevé I equation, the analytic continuation of the Borel sum can be explicitly described. And I'm talking about the linear system, the Borel resummation of the linear system. So this leads to connection formula for the linear system. And if one can connect this this linear Stokes data to maybe, for example, the parameters in the 2-parameter transseries, then one can obtain these transition functions like the ones that you would get for the nonlinear case. So it's basically connecting the linear transition functions to the nonlinear ones. For other Painlevé equations, as Professor Takei explained on Monday, we need a little bit more. So the method that they propose is this local reduction theorem that basically tells you that at any Stokes line of the Stokes geometry of this WKV solution, you can apply the Painlevé I transition functions, but then you have to play a little bit more with it. So, and I will explain to you what I'm going to do next. Don't worry. So basically, if one looks at the Stokes geometry before and after the transition, the Stokes geometry of this Q of this potential changes a little bit. And studying these transitions by imposing that these S0, S0 prime, S1, S1 prime are invariant, so they have to be the same, is basically how we get our transition functions. I'm just basically throwing to you results, of course, that come from the works of Takei in this case. And basically, he proposed these forms for these linear Stokes vectors. And basically, the isomonodromy condition just tells us that S1 is equals to S1 prime, and so on. So now we want to understand how these Stokes coefficients of the isomonodromic deformations are related to the resurgent Stokes data of the Painlevé I and Painlevé II equations. Let's just start by the Painlevé I case. So this connection was first done by Takei after his as a culmination of his work with Aoki and Kawai. And then Professor Iwaki explained or explicitly described this connection between the isomonodromic deformations and the resurgent data in a simpler setting and some unpublished work that he had. So he basically told us that there has to be this connection, and he did it for a simpler case. So we took this work by them, and we basically tried to connect the normalization that follows from the isomonodromy theory. There's a very natural way of writing these 2-parameter transseries. So if one tries to map their normalization coming from isomonodromy to ours, one sees that our sigma 1 that I was talking about, this transseries parameter, is related to their beta, while the sigma 2 is related to our alpha. And there are all these prefactors in front of them. And we will try to get our transition functions from the equations that I showed you before from Takei. After we made this connection explicit, and we try to, I mean, for a very simple case, just one of the transitions, a paper by Alexander and Marcel they are both here, appear, working more details on these things. So they probably are even better knowing than me in all these things. So the isomonodromy condition on S1, for example, let's choose the first one, reads like this. So you basically equate both sides of this equation. And now one can play around a little bit. And now using the map between alpha and beta and sigma 1 and sigma 2, one can obtain transition functions for mu. And of course, one can also derive this ρ0 being invariant from the Takei's equations. But I focus on this one because the shift is kind of the more important one. So if we write his transition functions into our variables, we see that in the end, we find exactly the same structure. So mu just gets a shift that is a log of some invariant quantity, which in this case is the 3 pi because of the change of variables between his equation and ours. It's just also rotating the plane. So it means that we find this exponential weight here that is just basically associated to one rotation. So that we are not looking at the 0 or the pi, we're looking at the 3 pi. So if one takes a look at this, we see that his transition function and ours agree. So this is very beautiful because we now have two different ways of approaching a crossing of a Stokes line and then having exactly the same results. And these results are very natural. It's just a shift in this very special variable, which, by the way, this mu is in Takei's convention and E for the people that are more familiar with the isomonodromy version of this problem. And then there is this rho that basically is constant. So this is very interesting, I mean, at least to me. Now, the case of Painlevé II is much more subtle. It's kind of harder because you have to play a lot with this theorem. And of course, there are some things that you were also discussing on Monday, especially regarding this Borel-Laplace resummation of this map, that it's not very clear and so on. But let me just be a bad boy and then just bang the theory again with this theorem. So in here, I'm presenting, and I took this from the paper by Aoki. This is like the Stokes geometry of the second Painlevé equation, in this case, the inhomogeneous. And you can see that we have these three sheets. And let me just, for simplicity and for reasons that you will understand later, go to the single cover. Okay. So if now go to the single cover, how does the theorem work in practice? So how can we try to do transition functions here? So we know that if we start from a point, let's say, imagine that we start in this transition, in this turning point, we will have here some Stokes connection formula. And this connection formula is given the same way, is given there, is the same one as the case of Painlevé I. The only thing that we have to change is that the normalization that we choose for the Painlevé II equation is a very specific one. So this Painlevé I transition function that goes there into Painlevé II is only valid if you choose the correct normalization. And then, but now you basically have to connect this to the way in which we wrote the transseries. And now, if you want to see what happens on this below line, you basically have to like change your basis from this turning point to this turning point. And this basically means that you have to change alpha and beta into some integration between the, so going from the upper turning point to the lower turning point of this quantity in the isomonodromy construction. But don't worry too much about this because we are lucky that these integrals are just 2 pi i's. And that's why I wanted to focus on the single cover. The integrations are much easier to perform. So if we start here again, so this is really like the turning point, or sorry, a transition function for Painlevé I. And this is the one that I'm using on the top Stokes line. Now I go to the below one, and these are the transition functions. The only thing I changed is this sign and this exponential of 2 pi I that appeared here, and alpha times beta is invariant under this change. So the rest of the equation keeps the same. And now if one does this, then now we can solve this system of equations. So we can connect the alphas and betas on top with the alphas and betas below. It's just solving a system of equations. But, and of course, we have to connect to our normalization. So the one starting on the upper turning point. And if we do this, let's just skip the details. There's a very long formula regarding logs of gamma functions and so on. But if we expand this, we should be able to see at least the first Stokes coefficient. And the reason why I'm giving you the expansion of this is because we don't have a lot of data on the single cover. So the only thing I can compare are the first numbers. So this is what I want to compare against resurgence. So now let's go back to these banging equations. So if we go to the inhomogeneous, I just want to recall how the lattice looks, because I'm always going to give you data in the form n11, n10, or n31, or stuff like this. So I want you to remember that these are just the coefficients of the Stokes data. So from the analysis before, the sign of pi alpha should be somehow this guy here, the simple one, because we just expanded either this one or this one, depending on the if it corresponds to a positive or a negative transition. And of course, if one tries to do this for the single cover, and you see here the numbers that I computed with this method that I told you before of angle contouring the pole plus the logs, if you try to do this, you see that up to very high precision, you produce either this sign and this another sign that clearly agrees with the computations that one can do from isomonodromy. And this is very interesting, because it seems that this theorem somehow is working. So unfortunately, we couldn't produce a lot on this side, so I cannot give you the whole transition functions for this single cover. But let's see what we can do on the double cover. So on the double cover, one can produce a lot of numbers for a lot of values of alpha, and then stare at these values for a long time, and drink a lot of coffee and realize that there's a pattern, or there's a form that reproduces all of them. And if one takes alpha to 0, one expects to reproduce the regular Painlevé II Stokes, and of course, this agrees. Perfect. But furthermore, this also coincides in some special cases in which alpha is n minus 1/2, n being an integer. And these cases have been studied by Alfredo Diaño, that has been here for most of the talk, so for most of the workshop. So there's still some computations, and he's a very mathematical person, so he really computed this. It's not that I was playing with patterns and numbers. So this also coincides with special cases, which is very nice. And identically, one can try to compute the counterpart, so the red guy to the blue guy. And of course, going to 0, one also expects to get the correct computation. And this is what we were getting. But also, this also coincides with some matrix model computation that exists for the inhomogeneous Painlevé equation that I haven't talked about because it's kind of outside of the scope. But just for you to know, there's also a matrix model computation that gives you this guy. So let's just continue. Of course, we have a bunch of other guys, and now there are 3 guys in all of these tables, and these tables are for different values of alpha, and one can stare a lot at these results and get a closed form version for all of this. And we can do this for a lot of values of alpha. And of course, these all coincide with this equation, these large asymptotic equations that Max was talking about, in which you can use these Bell polynomials to generate the whole first diagonal. So now we just need to understand how to go down. So now we go how to go to the diagonals. We need to understand how to go down on the first column. For that, we need more data, of course. And after taking a look at this data, we saw a pattern of this form. And now, okay, I can continue this pattern for any side and conjecture some form for the transition functions. So if we do this, now, again, we have to compute these rotations because these rotations now depend on alpha. And one can plug all of this again and feed it to the machine and say, okay, can you rotate again several times and go back to the original place with all these data that you have conjectured? And yes, we can. And I chose on purpose very random values for alpha, because you see these gamma functions and these digamma functions are very well behaved at certain points, especially numerically, but they are not very well behaved at very random points. So I wanted this to be robust. And all of these rotations go back to the same number to all the precision that I fed the machine. So unfortunately, we try to find this this closure of the monodromy orbits analytically, but this is a nightmare because it's like logs of gammas. So this gets really complicated, and there's like very weird things going on with gamma functions if one wants to prove this analytically. But in any case, since we couldn't perform the local theorem transformation method for the double cover, we wanted at least to give something on like a soft version of check on this data. So now what happened with the Q-deformed Painlevé equation? Well, I told you that this Miura map was connecting the inhomogeneous case that I've been talking about for a long time with the Q-deformed equation. And I mean, this connection can be done explicitly, and it's very simple, but we also wanted to see what we could do by basically banging also this Q-deformed Painlevé equation. And of course, in here, again, I mean, don't pay attention to the prefactor because it's basically due to different normalizations of the equations. But if I told you that alpha goes to Q plus minus 1/2, and I give you a sine of alpha, then of course you get a cosine. I mean, pi times alpha, of course. So we see that even the first guy that we have agrees. And one can also continue going down for this Q-deformed case and try to find some closed form for the next guy. And one can find it to very low precision, but still a very nice pattern. So one hopes that in the future we can find all of it. So finally, remember that at some stage I told you this is a workshop that somehow has to deal with strings and physics. So let's go back to this thing. So the Miura map, as I said, basically connects the Q-deform and the inhomogeneous case. So you could think as the Q-deform in terms of the inhomogeneous. And if you remember, Takei explained that there's this 0th order perturbative sector that basically has a double cover and a single cover, and these are related by this. Let me just go back for you to have the pictures. It's very far away, but I really want you to pay attention. Yes, here it is. So somehow there's like in the limit in which alpha goes to 0, these 3 points just merge in the center, and then this becomes a double cover and a single cover that are completely disconnected. So when we think about these open-closed string transitions, we always think about them in terms of this is a non-perturbative phenomenon. And of course, if you do resurgence and you listen non-perturbative phenomenon, you say Stokes data, Stokes transitions. But what happens in reality with this is if you really have solutions of this equation that at infinity behave as a closed string theory, and at minus infinity behaves as an open string theory, this relation of the open and closed string theory is not associated to crossing Stokes lines. It's associated to jumping sheets on these original perturbative determination of your perturbative series. And it would be very interesting to see, because this, as you see, if I try to do this and I tell you I have a, let me just go back a little bit, sorry for this. If I tell you, look, I want to start here and now I want to go here, there are several ways of doing this. Oh, sorry, let me just choose this one for simplicity. If I'm here and I want to go here, there are 2 ways of doing this. I can go from the top, or I can cross this branch cut. So there are 2 ways of going there, and one of them is associated to crossing a Stokes line, and the other one is just associated to going into a different sheet. And this open-closed string duality is associated to this second way of walking there, because you see, let me just go there. And I don't know if there's a way to tell from the original point how you went to the negative point. And I don't know if there's a way of like saying which path you took, but I think this is a very interesting thing to discuss. And there's some example of this that happens that it's very known in the literature, that is the Hastings-MacLeod case. And this is even a little bit weirder case. So now what we can see from here, you see this is the 4th cover and this is the double cover, is that this open-closed string duality seems to be associated to jumping sheets, not to crossing Stokes line. But I cannot guarantee that the crossing a Stokes line is not seen by this crossing a sheet. So I don't know if these 2 things can be connected somehow. So let me just discuss a little bit future directions. So one of the nice things that we could do from here on is, of course, write explicitly the connection between these double cover transition functions and try to find them that we know they close after 4 rotations, and try to get them from the isomonodromy problem. So applying this local reduction theorem. But it also seems that this open-closed string duality is associated to jumping sheets, as I said. So it's important to understand how to determine when this happens. Like, how can we determine that we jumped a sheet and not that we cross a Stokes line? So this is kind of another question that we can ask ourselves. But also, again, of course, I have to talk a little bit more about string theory. So the last thing that we could do is really, we know that this transseries is associated to some string theory. So there should be objects in the string theory that can compute these transseries monomials for us. And then we can compare and understand what the transseries means at the level of the string theory. But this is like a much harder problem, I would say. So thank you very much for your attention. I hope you like it. Yeah, that's it.
Questions, comments?
So this periodicity going through very weird numbers.
Yes.
It's reminiscence to what happens in a bias system. So all this has something to do with bias system periodicity.
I don't know what Weierstrass periodicity is.
Okay.
No, but you reminded me of something that I think it's very interesting. If you see, I always plot sigma 1 and sigma 2 because these are kind of the transseries, how Resurgence labels these transseries sectors originally. But if you take a look at them, you can see that they go from some completely unity number to some very suppressed number, again, very suppressed number again, and then a normal number. Let's just call it normal. But sigma 2 does the opposite. So it completely explodes and then goes back again to the same thing. So this thing is also telling us that maybe the best variables for understanding this thing is not sigma 1 and sigma 2 to understanding these transitions. It's the multiplication of them. Because if you see 10 to the 16, 10 to the minus 16, it kind of gets, again, back down to a number that is of order unity or a little bit more. And this is why I wanted to plot this sigma 1 and sigma 2 to see how weird it goes. But if you keep them multiplied, the transitions are much nicer. So the numbers are much more stable when rotating around. But it would be interesting to see what you meant.
Just make a comment. I might be wrong, but in the ODE-IM correspondence, you have that there's this relation between in the Y system between the functions when you have transitions in the Stokes phenomenon. And here, this is exactly what you have also. So it actually, there might be a relation between them. Sorry.
Yeah.
So thanks for a very nice talk. Earlier this week, we heard about this Cheshire cat resurgence idea.
Yes.
Here, if you send alpha to 0 in Painlevé II, do you have something similar where you can still see remnants of this extra solution, or does it completely go away?
Which extra solution? What do you
mean?
Well,
not really an extra solution, but when alpha is 0, everything simplifies a lot.
When alpha is 0, everything simplifies. But still, it's just like if you take all your equations and just send alpha to 0, everything works exactly. It's just the same value. It's just that there are some special values for which these gamma functions have poles. So alpha going to 0 is not it's a problem from the isomonodromy point of view because you have all these turning points that merge, and then it's not clear because this theorem only works when the turning points are simple. So from the isomonodromy picture, it's really bad to have alpha going to 0, but there are a lot of alpha values for the single cover or the double cover that pose problems that are not 0. And this is a lot, it is very much associated to these special function solutions that of the 80 type and these Hastings-MacLeod solutions and all of this. But yeah, there are very special values of alpha in which the transitions are not as nice, or they can even blow up or just be 0 or things like this. So this is more or less how I would say the alpha going to 0 limit is. But all the things that we did here reproduce, so all the transition functions for the inhomogeneous double cover, which is the one that I worked on the most, if you take the value alpha going to 0, you produce all the transition functions for the original Painlevé II equation, the homogeneous one.
So there's nothing like in the large order behavior that suddenly disappears.
The only thing that alpha does in the large order behavior, for example, for the perturbative, is that the large order behavior, the 2G factorial, starts dominating later on. So basically, instead of having this factorial growth initially, like with the, I don't know, in the first 100 coefficients, you will already see this factorial behavior. If you keep increasing alpha, you will have to go to much higher G, such that this G factorial dominates. And the same thing happens with the Q. And that's why sometimes when you see precision for example, for these guys, alpha equals 0 has a very nice precision, but 1/2 has less precision and so on, because I kept fixed number of coefficients. It means that asymptotically they're worse approached because alpha is better, is greater. So it's kind of counter-dominating this G factorial. It's just that at the beginning, but if you really go to high G, it basically, it's washed away by the derivative.
Any other questions? Can I just ask
Yes.
one curiosity, which is when you showed the values of the monodromy for sigma 1, sigma 2 different times, it always looks like apart, independent of what you chose first, that the product in the mid sections of sigma 1 to sigma 2 is always of order 1. Does this always happen?
It depends on the initial conditions that you choose, of course. Like it will always be more or less of the order of 12 in this case.
So the
because
product of those will be of the same order as the.
Yes. So it depends a lot on if you go to the transition functions. Yeah, this was much further behind. Here, it depends a lot on what this contribution is. So it depends a lot on these rows at any transition. And depending on these rows, this can change a lot or not. But normally what it happens and what we were seeing is that you get something like the original quantity, now you get plus some quantity, then plus some a different quantity, then you subtract the second one, then you subtract the first one, and then you go back to the same. So it's always like something, and then you add something, you add a second one, then you subtract the second one, and then you subtract the first one. So it's always like going and then coming back. And that's what it normally happens. Like, yeah.
Thank you.
Yeah.
Just add to your question. I think there's also kind of a multi-valuedness in there, right? So this, I think the alpha beta do indeed stay at unity, but they can, there's a certain multi-valuedness due to the logarithms, which are also in these connection formula. So.
Yes. Also, every time I plot this, I plot the transition functions. I'm always taking them back to the original. So I'm always, every time. Exactly. I'm always going back to the 0th direction, for example, or the 0th above, 0th below. Exactly. So if you go to different branches, you always have to pull it back to the original in case if you want to compare transseries. So I wanted to keep the same transseries, so the same phase on the transseries, and I reabsorbed all the phases in the sigma 1 and the sigma 2.
I think in fact, if you take a different branch, you could get an alpha and beta, which is much more closer. I mean, we've also tried to plot these things, and when you go to a different branch, you'll get an alpha, which is extremely small, and a beta, which is extremely large.
Yes.
But if you jump to different branches, there's always like a sweet spot branch where the alpha and beta are approximately same order. So it's also, again, a choice of branch. Yes,
that's true. Also, but also like I think that the difference between your alpha and beta and my sigma 1 and sigma 2 is also these exponentials. So for us, it was kind of harder to do because these exponentials, like these 3 to the -3 alpha times beta, sometimes would put a lot of problems in choosing nice sweet spots in the sigma 1, sigma 2 plane that basically kept more or less their size. So for us, we also tried this thing that you say, that to keep alpha and beta, or like sigma 1 and sigma 2, to reasonable numbers along the whole transitions. But it was kind of hard because of this difference in change of variables.
Any other questions, comments? If not, let's thank Roberto again. So before we go for lunch, I think that Mike Berry wanted to just say a couple of minutes.
Yes, I have to leave after lunch, but I do want to make a comment. it's been enormously impressive to see old ideas in asymptotics applied to much more sophisticated concepts with such, in quantum field theory I'm speaking about, with such technical and numerical virtuosity. But there's one fundamental aspect of asymptotics that I haven't seen applied, at least not in this meeting. And this came up in conversation with Nalini, but it's more general. And I'm speaking about uniform approximations where, instead of having a power series in a large parameter multiplying exponentials, which you've seen time and time again, they multiply more sophisticated functions which can accommodate coalescences of saddles as other parameters vary. Now, of course, these coalescences can happen in a number of different ways, topologically different ways, and this is all well understood and understood even explicitly. Now, these uniform approximations, when you apply them to concrete problems, are enormously powerful. They're incredibly accurate because they apply not only near the coalescence, but with stretched variables, well understood, also far away where they match on to the familiar approximations where the saddles are separate. And Chris Howells and I discovered that these uniform approximations with their corrections also obey resurgence relations. And so that's in the world that we've been speaking about here. So there are lots of parameters, of course, in quantum field theories. So I'm sure that these various classes of much more sophisticated approximations will find application. So that's my comment, just as something I haven't seen, which in other applications of asymptotics is now fairly standard. That's all.
So we'll reconvene at 1:30.